Before we get into questions on homework 1.4, let's review what it means to multiply a matrix A by a vector X. Here's the way we want to think about it. We want to make a linear combination of the columns of A using the entries in X as weights. Make a linear combination. AX is a linear combination of the columns of A using the entries in X as weights. We're going to make a linear combination of the columns of A using the entries in X as weights. It's really important that we think about this matrix multiplication as making linear combinations of the columns of A and not just mechanically getting ourselves through the multiplication to find out the numbers. So for example, if I have, let's say, by columns, the matrix A is 1, 3, 3, 2, negative 4, 1, and I want to multiply this by the vector X, 1, 2, 1. So I'm going to multiply the matrix A, which is 2 by 3. The columns are 1, 3, then 3, 2, and negative 4, 1, by the vector X, which is 1, 2, negative 1. I'll take 1 times the first column. It's going to be 1 times the first column, 1, 3, plus 2 times the second column, which is 3, 2, plus 1 times the third column, which is negative 4, 1. I'm making a linear combination of the columns of A using the entries in X as weights. So I get total of 1, 6 minus 4 is 2, 3, 4, and 1 is, I forgot what that was, 3 and 4 is 7, plus 1 is 8. Let's just go with that. So when I multiply the matrix A by the vector X, I get the vector 2, 8. I've made a linear combination of the columns of A using the entries in X as weights. That's how we want to think about multiplying matrices. The way we mechanically multiply matrices is we go across the row and then down the column. And we just make, for those of you who've been in Calc 3, we make a dot product. We go 1 times 1 plus 3 times 2 minus 4 times 1 is 2. 3 times 1 plus 2 times 2 plus 1 times 1 is 8. That's mechanical. It ignores all this linear combination business and is therefore way less valuable than thinking about linear combinations. The typical way, we'll see on the upcoming linear combinations quiz that's framed in matrix multiplication, the typical way to name the columns of a matrix is just by using a lowercase version of the matrix name. So lowercase a sub 1, A2, and A3 are the columns of the matrix A. That's typically how we name the columns of a matrix. So in this case, I'm writing A as square bracket A1 space A2 space A3. Notice that when I'm writing A as a matrix, I'm not putting commas in between the columns of the matrix, A1, A2, and A3. I'm just separating them by space. This is because when I write a matrix, I don't put commas in between the columns of the matrix. So this is a typical naming scheme for the columns of a matrix. So that's one thing to note, how we think about matrix multiplication. Another thing to note is how we name the columns, because oftentimes we just name a matrix A, and it's up to us to call the columns of the matrix something if we need to. Thing number 3 to think about is that however many columns we have in the matrix, that's the number of entries we need to have in the vector. So the number of columns of the matrix must equal the number of entries in the vector. So note, if the number of columns of A is not equal to the number of rows in X, then the product AX is not defined. To multiply a matrix by a vector, the number of columns of the matrix has to equal the number of entries in the vector, because I have to have a weight for each of the columns. I'm trying to make a linear combination. I need a weight for each of the columns. That's another way to think about it. That is, we need a weight for each column. We need a weight for each column. So if I wanted to multiply this matrix A, 1, 3, 3, 2, negative 4, 1, if I tried to multiply that by the vector just with 2 entries, like 5, 7, this product is not defined. I don't have a weight for each of the columns. The matrix A is 2 by 3. The vector X is 2 by 1. And we have no match in the number of columns of A and the number of rows of X. A is 2 by 3, and X is only 2 by 1, and 3 is not equal to 2. We cannot make a linear combination of these 3 vectors with only 2 weights. Any questions? Whatever scheme you might be thinking of to try to multiply this matrix by this vector, someone else will think of it think of a different scheme. You won't be coming up with the same things, and that's not acceptable. One person can't be saying 2 plus 3 is 5, and another person be like, oh, 2 plus 3 is 6. That's not acceptable. Someone has to be wrong. Any questions? Okay, so with that in mind, let's discuss any questions from homework 1.4. Any questions on homework 1.4? Go ahead and type those in the chat. Let's see. Is there any surprises that I wanted to go over? Remember, most of these questions, we're going to be looking for an augmented matrix of a matrix equation or a vector equation or a linear system. And if it's just a question of whether something is consistent or not, we just want to make sure that we do not have a pivot in the rightmost column. Any questions in homework 1.4? All right, so let's take a look at problem 17. So we have this matrix A, which is 4 by 4. Let's write that down. So let's see, 1, 4, 17. Here's the matrix A. By columns, it's 1, negative 1, 0, 2, 3, negative 1, negative 4, 0, 0, negative 1, 2, 3, 3, 1, negative 8, negative 1. So we have this, oops, crooked, there we go. We have this matrix, and we want to know where the pivots are. So let's find the pivots. Note that this is the matrix A. This is not an augmented matrix. We should make a note of that first. We have questions about how many pivot positions are in A, And does the equation AX equals B have a solution for each B in R4? So notice that this is not an augmented matrix. This is the first time we're going to start encountering matrices that are not necessarily augmented matrix. So this is not an augmented matrix. So if we're going to think about the variables that are attached to each column, this does have an x1, an x2, an x3, and an x4. And then if an augmented matrix would have another column out here with the constants, but we're just looking at the matrix A, the coefficient matrix. Let's find the reduced or echelon form of this matrix so we can find out where the pivots are. So second matrix, math B. So I got by rows 1, 3, 0, 3. Close the row, open the next row. -1, -1, -1, 1. Close the row, open the next row. 0, -4, 2, -8. And then last row, 2's, 3, 0, 3, -1. Close the row, close the matrix, close the command, and then check to see I've got everything. 1, 3, 0, 3, -1, -1, -1, 1, 0, -4, 2, -8, 2, 0, 3, -1. So this is going to make some exciting YouTube. Dude enters matrix in calculator, hits enter. Rad. So here's the reduced row echelon form of the matrix A. I'm going to write it down. I'm not going to say equals because this is not equal to this matrix. I'm going to say we perform some row operations. And by columns, our reduced row echelon form is 1, 0, 0, 0, 0, 1, 0, 0, 1.5, -0.5, 0, 0, and then 0, 0, 1, 0. So we see we have 3 pivots in A. First row, first column, second row, second column, third row, fourth column. So A has 3 pivot positions. We don't have, the third column is not a pivot column. Any questions? What this means is that we have a row in A that does not have a pivot column. That means in an augmented matrix, it's possible that we have a pivot in the rightmost column. There are some choices of B that will drop a pivot in the rightmost column of an augmented matrix. A has 3 pivot positions. That was the first part of the question. So what we can conclude is the augmented matrix A, B, since A has 3 pivot positions but 4 rows, the augmented matrix A, and then if we put B on the other side, might have a pivot in the rightmost column. Might have a pivot. Because A has 3 pivot positions and 4 rows. That open row down here means that if we made an augmented matrix with A, we might have a pivot in the rightmost column of an augmented matrix. What that means is that AX equals B is inconsistent for some choices of B. AX equals B is inconsistent for some B in R4. We know it's not an augmented matrix because it's the matrix A, and the question framing says, does the equation AX equals B have a solution for each B in R4? And so this whole matrix A is being used as a coefficient matrix. So the augmented matrix would have a fifth column for the constants. So by context, that's how we know it's not an augmented matrix. So that's how we know that AX equals B is inconsistent for some B in R4. Equivalently, we could say that AX equals B is not consistent for all B in R4. We have to look at these two sentences. And we have to make sure that we understand how they're equivalent and how we can't just take the word inconsistent and not consistent and replace it with the word inconsistent in all cases. AX equals B is inconsistent for some B in R4, but that also means it's consistent for some B's in R4. It's also consistent for some B in R4, because some choices of B, we will not have a pivot in the rightmost column, because we might have a pivot, but we also might not. So we could say that AX equals B is inconsistent for some choices of B in R4, or we could say that AX equals B is not consistent for all B in R4. Here's where English really starts being a jerk of a language. We cannot say that AX equals B is inconsistent for all B in R4. Even though you look at not consistent and say, I'll say inconsistent. We can't do that, because then we're wrong. We're just saying AX equals B is not consistent for all B in R4. It is consistent for some B in R4, because it might have a pivot in the rightmost column, but it also might not. But the augmented matrix see, I'm turning the A into an augmented matrix by writing A and then saying B on the other side. Might not have a pivot in the rightmost column. Might, that might not. Therefore, AX equals B is consistent for some B in R4. And inconsistent for other B in R4. We got to be really careful about when we say things for some and when we negate things for all. Any questions? For B, use the same thinking. In part B, which is just a different matrix, can every vector in R4 be written as a linear combination of the columns of matrix B? That's the same as asking the question, is Bx equal B consistent for all B in R4? I use different cases of B that you can't hear when I'm speaking them. This is another reason that English is a terrible language for math, and we should just try to learn math and all of it.
Who likes $40 round trip? Who likes $40 round trips?
It's a lie, I'm sure, but
Any questions? So another thing, as far as DVD bonus material goes,
mailing list.
another thing to note as far as DVD bonus material goes is that the columns of A as a set of vectors are not linearly independent, because the third column is a combination of the first two columns. Notice that because we did not get a pivot in this third column, so we're going to DVD bonus material. Oh wait, let's upgrade to Blu-ray bonus material. The columns of A are not linearly, I spelled I wrong, independent. The third column is a combination of the first two columns. The third column is just a linear combination of the first two columns. So if I name the columns in the standard way, A1, A2, A3, A4, we see that A3 is just 1.5 times A1 minus 0.5 times A2. A3 is a linear combination of the columns A1 and A2, so the columns of A are not linearly independent. Any questions? How's everybody okay? It only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time. That is a correct observation. The x equals b part says that the matrix A is a coefficient matrix and not an augmented matrix. How's everybody okay? What's not inconsistent? We can't use the word it. I don't know what you mean by the word it. If it's not, so the equation, the matrix equation AX equals B is not consistent for all B in R4 because there might be a pivot in the rightmost column of the augmented matrix. But but we're not guaranteed to have a pivot in the rightmost column. So it's possible that we don't have a pivot in the rightmost column of the augmented matrix. Let me do a smaller example, and we can explore this further, because this is an important distinction that we may need to make. This is an important thing that we need to get around. I'm going to make a smaller example. So I'm going to make a small matrix A. And the matrix A is going to look like 1, -2. And then the second column of matrix A is going to be, let's see, -3, 6. What do you notice about this matrix A? Let's make sure I did it right. Okay, yeah. What do you notice about this matrix A? The columns of the matrix A are collinear. The second column is just -3 times the first column. So that's what we want to notice. This is why I picked a small one. It's easy to see these things, right? So notice that the columns of A are collinear. Oops, I spelled A wrong. So the columns of A are not linearly independent. So we'll say they're linearly dependent. That is collinear. Because there's only 2 of them, we can go with the collinear business. The reduced row echelon form of the matrix A is going to be 1, -3, and then by rows, the first row will be 1, -3. Then if I do 2 times the first row plus the second row, I get 0, 0. So I did not get a pivot in the second column. The reduced row echelon form of the matrix A tells me that A2 is just -3 times A1. So if I name the columns in the standard way, here's A1 is 1, 2, and A2 is -3, 6. The reduced row echelon form is telling me that A2 is just -3 times A1. That's what this reduced echelon form is telling us. So if I put this matrix as a coefficient matrix, the equation AX equals B is sometimes consistent and sometimes inconsistent. Because I didn't take up all the pivots in the coefficient matrix, there might be a pivot in the rightmost column of the augmented matrix. Since we don't have a pivot in every row of the augmented matrix, since we don't have a pivot in every row of the coefficient matrix, the augmented matrix might have a pivot. In the rightmost column. Spelled P wrong. So AX equals B is consistent for some choices of B and inconsistent for other choices of B. AX equals B is consistent for some B but inconsistent for others. So for example, if I take AX equals, let's say, 10, -20, that's a consistent equation. If I look at the reduced echelon form, even though there's not a pivot in every row of the coefficient matrix, this particular choice of B is not going to put a pivot in the rightmost column of the augmented matrix. So the augmented matrix would look like by columns 1, -2, -3, 6, and then 10, -20, augmented matrix. And the reduced echelon form, the first row will still be 1, -3, 10, and then the second row zeroes out. We do not have a pivot in the rightmost column of the augmented matrix. But if I make a different choice of B, we'll get an inconsistent equation. So AX equals, let's say, -6 and then not 12, say not 12. I need a number that's not 12, 11. That's not good. I was struggling to come up with a number that wasn't 12. Oh well. The augmented matrix by columns will be 1, -2, -3, 6, and then -6, 11. And the reduced echelon form, the first column will be 1, 0. The second column will be -3, 0, because those cancel out. The third column will be -6, The third column will be, I'm going to do the first operation. Sorry, this is not the reduced echelon form. -6, and I have to multiply it by 2 and add it to this one, -1. So we ended up with a pivot in the rightmost column of the augmented matrix. So if the coefficient matrix does not have a pivot in every row, there might be a pivot in the rightmost column of the augmented matrix. And that would correspond to an inconsistent matrix equation. Any questions? We've got to be very careful about how we say things, because math is a very precise language. So if the coefficient matrix does not have a pivot in every row, then the matrix equation AX equals B is not consistent for all B in Rn, whatever it happens to be. Yes, if there was a pivot in the second row, if there's a pivot in the second row of the coefficient matrix, there's a pivot in all the rows of the coefficient matrix, then the equation AX equals B could not possibly have a pivot in the rightmost column. The augmented matrix could not possibly have a pivot in the rightmost column. So if I make a coefficient matrix A, if I make this my coefficient matrix A, 1, -2, and then -3, 5. In this case, the second column is not a multiple of the first column. The reduced echelon form of A is 1, 0, 0, 1. There's a pivot in every row of the coefficient matrix, so there could not be a pivot in the rightmost column of the augmented matrix. A pivot in every row of the coefficient matrix. A pivot in every row of the coefficient matrix means there cannot be a pivot in the rightmost column of the augmented matrix because we've used up all the pivots. Therefore, AX equals B is consistent for all B, in this case, R2. Any questions? Like I said, it's a lot to think about. It's only a lot to remember. It only seems like it's a lot to remember because it's a lot to remember, and you have to remember it, all of it, all the time, and perfectly. And then you have to write the right thing. How's everybody, okay? Let's pause the recording and talk about what we should do next.